Hello and welcome. In a previous video, we took a look at the definition of the double integral of a function of two variables. And what that allowed us to do was to be able to find something like the volume under a surface over the xy plane, but restricted to a rectangular region. In this video, we're going to be taking a look at the double integral of a function of two variables over a more general region in the xy plane. So let's start by recapping a little bit about what we already know about the double integral. We know that if we have a continuous function f of xy over some sort of rectangle, and we have these two different notations. We have our set notation using inequalities, or we can use a Cartesian product of these two intervals, a to b and c to d. Well, we can turn that double integral into iterated integrals of the form dy dx or dx dy, and they're interchangeable. And that's mainly because of that restriction that R is a rectangular region. Well, what if we wish to integrate over a non-rectangular region? What's going to majorly change here is that our boundaries are not going to be simply constants. Those are just vertical and horizontal lines on the xy plane. And this time around, our boundaries are actually going to be curves on the xy plane. Let's take a look at a couple examples. In this first type of region, let's suppose that we have two nice functions of the form y equals g of x. Maybe we'll have g1 of x and g2 of x. And our region is bounded by those two curves over some interval for x. Maybe our region is bounded by the intersection point of these two curves, and that will happen when x equals a. And maybe our region only goes as far as x equals b. That would give us this nice shaded region in between these two curves. You can imagine that if I were to fill this in with vertical stripes, that the top and bottom of these vertical stripes are always going to be bounded below by the red function and bounded above by the blue function. We call that y simple. If you want to use our set notation here, then we can just use an inequality from one constant a to another constant b for our values of x. But as we see, traveling from a to b, at an arbitrary x value here, our y boundaries are not always going to be the same. These 2 points that form the boundary top and bottom of every little vertical section of this area is going to be bounded below by g1 of x and bounded above by g2 of x. And that's where we get this inequality from. Now, how do we actually turn a double integral into an iterated integral over this region? If this region is D and we want to look at the double integral of some function f of xy over D, then the first thing we're going to do is integrate this function with respect to y. We're going to integrate f of xy from g1 of x to g2 of x. Now the process here isn't really any different than iterated integrals over a rectangle. We're looking for an antiderivative with respect to y, and then we're going to evaluate at g2 of x and at g1 of x and subtract. When we do that, we're going to end up with a function that only involves x in its expression now. That allows us to look at the definite integral of that expression with respect to x from a to b, and we will end up with a numerical result again. Now, not every region is going to be y simple, because not every curve on the xy plane can be easily written as a function y equals g of x. So let's take a look at case 2. In case 2, let's suppose that we have a region bounded by two functions of the form x equals h of y. We'll use h1 of y and h2 of y. And here's our region bounded by those two curves. And we can see that, well, it kind of makes more sense to look at horizontal little cross sections. At any given y value, we have a left boundary on the green curve, and we have a right boundary on the purple curve. And our y values are simply going to range from this lower intersection point, let's say at y equals c, up to this higher intersection point, let's say at y equals d. That means that we can define this region, let's say d, in interval notation, where y ranges from c to d, and for every given y value, x will range from h1 of y to h2 of y, making sure that we have a lower value of x on the left to a higher value of x on the right. And similarly, we can evaluate a double integral over this type of region as well. Given a function f of xy, integrating it over the region D, we're going to first integrate with respect to x. We'll look for an antiderivative with respect to x and evaluate at these two functions of y. And that will leave us with an expression that only involves the variable y. From there, we can look at the definite integral of that expression from y equals c to y equals d, and again, get a numerical result. Now the trick is to take a look at the region and understand whether or not you would want to take a look at horizontal cross sections or vertical cross sections. By drawing a dotted line through every given x value in the region, will you always have the same top function and bottom function? If that's the case, use dy dx. If you're going to be looking at dotted cross sections horizontally throughout the region from bottom to top, and you always end up with the same two curves, left and right, then you should probably be using dx dy. And some regions can be simple in both x and y, and some regions may not be simple in either. If that's the case, then we know from properties of integral, we can always separate that region D into smaller subregions that may be x or y simple on their own. Let's take a look at an example of a region and set up both of these different forms, dy dx and dx dy. In this example, let's take a look at finding the volume of a region that is under the plane z equals 2x plus y, and over a region on the xy plane that is bounded by a line, y equal 2 minus x, and a parabola, x equal 4 minus y squared. And you're going to see that one of these is a function of the form y equals g of x, and one of these is a function of the form x equals h of y. So it might not be immediately obvious whether or not you want to set this up as dy dx or dx dy iterated integrals. That's why it's always a great idea to sketch the region. It's a fairly simple parabola to graph, and it's also a fairly simple line to graph. And looking at this region, hopefully you can determine which of the two orders is going to be easier to set up. But let's try both of these different orders, and we're going to quickly find that one of them is much more work. Let's start off with y simple. It's often the case that we like to have functions of the form y equals g of x because that's what we're familiar with from single variable calculus most of the time. In this case, we're going to need to figure out what our interval is for x from one value to another. And then at each of those x values determine whether or not the boundaries on y are consistently the same functions. So let's find these two intersection points where the red and blue curves both meet each other. And that's fairly simple to do. We can plug our blue function x equals 4 minus y squared into our red function y equal 2 minus x and solve for the intersection point. We just need to expand that out, collect terms, and we should get a quadratic. And we'll quickly find that the two values that solve that quadratic are y equals minus 1 and y equal 2. Okay, well, we need an interval for x, so what if we were to just plug those values of y back into our y equals 2 minus x or x equals 4 minus y squared curves? That will give us our coordinates. If y is equal to 2, then x must equal 0, and if y equals minus 1, then x has to equal 3. Finally, you can see that we actually need to integrate all the way from 0 up to the vertex of this parabola, so we'll probably need to use that point here as well in case 1. And the vertex of that parabola occurs when y is equal to 0 and x is equal to 4. Okay, well, if we're going to set up something of the form dy dx, then we can see right away that our x has to range all the way from the intersection point here, where x is equal to 0, all the way up to the vertex here, where x is equal to 4. But at various different values of x, we can see that the boundaries are not always consistent. In some cases, the boundaries are the red curve for the bottom and the blue curve for the top. However, later values of x, we can see that we have blue curve for the bottom and blue curve for the top boundaries of those cross sections. That means that the boundaries are not consistent over the entire region, and it is not y simple on its own. But we can fix that by splitting this region up into two separate regions that are both y simple. This purple division line starts at the intersection points of the red line and the blue parabola. And now on the left, we have a y simple region. Maybe we'll call that D1. On the right-hand side, we have a y simple region as well. Call that D2. So we'll have to split up a double integral over D into a double integral over D1 plus a double integral over D2. Well, let's start off with that. Our double integral over D of the function 2x plus y, dA, will need to be split up into the double integral of 2x plus y over d1 and d2 separately. Okay, let's take a look at d1 now. We can see that the values of x range from 0 to 3. That's when we get to the intersection point, and that's the cutoff of region D1. We also see that the bottom boundary for any given value of x from 0 to 3 is y equal 2 minus x. The top boundary for that region D is the top half of the parabola x equal 4 minus y squared. That means we're going to have to solve for y there. And we can rewrite that function as being y squared equals 4 minus x. The top half of that parabola is when we square root both sides and only take the positive value for y. That leaves us with the top boundary as the square root of 4 minus x. And that's how we can set up that first double integral. Our very first iterated integral from x equals 0 to 3 will have the function y equals 2 minus x for the bottom boundary and y equals root 4 minus x for the top boundary. Now let's take a look over here at D2. In this case, our values for x only need to range from 3 to 4 to complete the entire region that we're integrating over. The boundaries for y will start from the bottom half of the parabola, which is the negation of the root of 4 minus x, and go up to the top half of the parabola, which will be the positive root 4 minus x. That's how we'll set up that second integral. We have the boundaries on x from 3 to 4, and the boundary on y from the negation of the root of 4 minus x to positive root 4 minus x. Now, as you might have already guessed, trying to set this region up as y simple is probably not the best way to go. The only way to do it is to split the region up into two separate regions that are y simple. That already sounds like a lot more work. Not only that, these separate regions don't have the greatest boundaries. If the boundaries are roots of polynomials, for instance, then that means we're going to be trying to look at the next iterated integral, the x component, and that definite integral is going to involve all kinds of potential substitutions, which may or may not be that easy. So why don't we try seeing what horizontal cross sections can do here? Now the good news is we've already got our intersection points. We've discovered the intersection point 0, 2, and another intersection point 3, -1. And let's see what happens as we vary our y values from -1 up to 2. At any given value of y, if we were to just have a horizontal cross section, we'd have a left boundary and a right boundary from the red line to the blue parabola. And we can move that same y value a little bit further up, and we see we always have consistent boundaries, red line to blue parabola, left to right. Well, that makes it x simple throughout the entire region then. We can say that this region has y values ranging from -1 up to 2, and at every given value of y, our x values will always range from the red function on the left to the blue function on the right. However, our red function here is of the form y equals g of x. We still need to solve for x, but luckily this is a linear equation. X is simply just equal to 2 minus y. So our boundaries on x range from 2 minus y up to 4 minus y squared. Those had better be functions of y because at any given value of y from -1 to 2, the x boundaries are not constant numbers. They depend on the current value of y. This means that we can turn our double integral of 2x plus y dA over the region D into the iterated integral where y ranges from -1 to 2 and x ranges from y minus 2 to 4 minus y squared for each of those y values. This is much easier to evaluate, so let's try looking for the antiderivative and iterating one step at a time. In this particular case, since we're not dealing with a rectangle, there's no potential option for splitting up into integrals of x and y separately. We really need to integrate with respect to x first and evaluate at these two functions of y so that we can take the resulting expression and integrate from y equals -1 to 2. Okay, the antiderivative of 2x is just going to be x squared, and an antiderivative of y with respect to x is going to be xy. We're just treating y as a constant, just like treating the 2 as a constant. We'll have to evaluate that from x equals y minus 2 to x equals 4 minus y squared. And if you ever find it a little confusing as to what you're trying to substitute into, you can always actually write the x equals in front of that expression. Substituting in x equals 4 minus y squared, and then substituting in x equals y minus 2 and subtracting. You can see that we end up with an expression just involving y at this point in time. From this point, we'll have to try to look for an antiderivative with respect to y. That's not going to be exactly a lot of fun in its current form, so I would recommend expanding the entire expression out. That leaves us with a nice polynomial, and we can find an antiderivative with respect to y and evaluate the definite integral from y equals -1 up to 2. After a whole bunch of power rules, evaluating the expression at 2 and -1, finding the difference, gives us 477 over 20 as this volume. Well, now that we know how to evaluate double integrals over rectangular regions as well as general regions, let's take a look at a couple of the basic properties of double integrals just in general. Just like with single variable, single integrals, whenever we have a constant multiple, we can pull that up front of the double integral and then evaluate the double integral of simply just the function f over the area d. Likewise, just like single variable calculus, if we have a sum or difference of two multivariable functions and we're integrating as a double integral over the region d, we can always split that up into the double integral of f over d plus or minus this double integral of g over the region d. What's also probably fairly obvious is that if the area of this region is 0, then the double integral of any function over that region is also 0. This last property might not be quite as intuitive, but if we were to take a region D and look at the double integral of a function equal to 1 over that region, then the volume that we're getting is going to be the area of the base times height, which is just the area of the base times 1. And that just gives us the area of the base. It gives us the area of the region D. So we can actually set up a double integral to get areas instead of a single integral to find areas like we did in single variable calculus. Now let's try an application that involves that second property. If we're looking for the volume of a region bounded by two functions or two surfaces, z equals f of xy and z equals g of xy, by the second property, the volume of the region between those two functions is certainly just going to be the volume under the higher surface minus the volume under the lower surface. And we can combine those two together into one single double integral of f minus g. Let's start off with two fairly easy functions. Two planes, z equals x and z equals 5. And let's see if we can find the volume between those two planes, but over a region that is bounded by a parabola and two lines, y equals x squared, y equals 25, and x equals 0. Now, what can be a very tricky part of the problem here is trying to visualize what this region looks like. It is some kind of solid, and it has one surface on the bottom that is at a slant, z equals x, and one surface that is flat, z equals 5. Why don't we start off with those two surfaces? And what I might suggest to be able to come up with this kind of sketch is actually to rotate the axes slightly. And we can have x to the right-hand side of our page and z to the top of our page, so you can see a nice diagonal line, z equals x. And z equals 5 is a horizontal line. Then we simply just need to extend those two lines outward in the positive or negative y directions. So I've turned those into planes here with this kind of interesting perspective. But what about the region? The region that we're actually integrating over is on the xy plane. You can see x is pointed to the right-hand side of the page and y is pointing into the page. Let's see how that transformation there of the graph of y equals x squared would look like when we have the slanted xy plane there. In the same orientation, you can see that this red curve is y equals x squared. It has a parabolic shape. We have our line x equals 0, which is just a nice straight line, and we have the line y equals 25. There's our region D, and it might be a bit of a tough grasp to understand how we turn a solid over that region bounded by these two surfaces. Don't worry, I'm going to try putting this all together in Maple for you so you can take a better look at what the surface really looks like. But you can imagine that we have sort of a triangular cross shape when looking at this region from the xz plane, and looking down at the xy plane, we have kind of a triangle with a parabolic side instead of a third flat side. Now, setting up the actual double integral isn't going to be that bad. The volume will be given by the double integral over the region D of top surface minus bottom surface. Z equals 5 minus Z equals X. But now we have to figure out how we're going to iterate this integral over the region D. Let's see whether or not this should be x or y simple. If we're going to take a look at dy by dx form, then what we're going to do is starting at x equals 0 and moving up to the intersection point of the purple and red lines, see whether or not the boundaries are always consistent. At an arbitrary x value, you can see that our lower value of y is bounded by y equals x squared, and our upper value of y is bounded by y equals 25. And that is the case for any arbitrary x in that region. So it seems to be y simple. We might also try to see if it's x simple. In this case, we're going to be looking at, for any value of y ranging from, it looks like y equals 0 up to y equals 25, whether or not the boundaries for x are always consistent. Taking a value of y just arbitrarily somewhere in that region, we see that the lower bound of x is 0 and the upper bound of x is given by the function y equals x squared. So it is consistent, but this function y equals x squared isn't in the form of x equals h of y. So even though it is x simple, it is probably easier to go with a y simple region and try to form an iterated integral of the form dy dx. In this case, we see that x will range from 0, which is this yellow line, all the way up to the intersection point of the purple and red lines. Let's see if we can just set y equal 25 equal to y equal x squared and solve for x. Taking only the positive value, that tells us that x is equal to 5. And we know that y is equal to 25, and that gives us our coordinates. That means that we're going to iterate from x equals 0 up to x equals 5. And at any given value of x in that region, our y values will always range from the red function up to the purple line. So our y values will be bounded below by x squared and bounded above by 25. In this case, 25 is a constant because that y value is the same for any given value of x from 0 to 5. This allows us to finally set up that iterated integral. We are going to evaluate the definite integral of 5 minus x from y equals x squared up to y equals 25 first. That'll give us an expression just involving x's, and then we'll look at the definite integral from x equals 0 to x equals 5. Good news here is that 5 minus x is treated as a constant with respect to y, so we can actually move that out front of this first definite integral. Now we just need to look at the definite integral dy with respect to y, x squared to 25. The antiderivative is y, and we'll evaluate from x squared to 25, giving us 25 minus x squared. Now we need to look at the product of 5 minus x and 25 minus x squared, and that will again just give us a nice polynomial. And once we've expanded out, we can look at the antiderivative with respect to x and evaluate the definite integral from 0 to 5. That's a bunch of power rules again, and luckily evaluating at 0 is quite easy, so in the end we really only need to evaluate at 5 here. That gives us 3,125 all over 12. Now, as promised, I'm going to show you what this region looks like in Maple. And that's mostly because I know how difficult it can be to try to sketch the region on your page. Having a tool like Maple or other 3D plotting software is just absolutely vital for being able to understand what you're really doing here when you're evaluating a double integral. So I've got a couple different little commands ready to go here, and the first one is literally just evaluating that integral to check our answer. You can do that using the calculus palette on the left hand side. There's a double definite integral right there, so you can just click on it and fill in the boundaries. And if you need to change order, dx dy is also an option. So we'll go ahead and we'll evaluate that, and sure enough we get 3,125 all over 12. I'm also going to include the plots package here, and the first thing we'll do to draw these surfaces is use the implicit plot3d command. And I've got the equations all here, and I'm just kind of picking a region in R3 that should hopefully give us the solid that we're looking for, with some options to match some nice colors and also try to give us a little bit of a better style of these surfaces. And here is that region, and you can see we have all the different surfaces color-coded, and it's hard to sometimes find the origin. You can see X and Y are there. The origin is actually at the back. We need to rotate this around so we can get a better sense of our same view that we draw on paper. Here's the origin 0, 0. And as Y increases and X increases, we're going into the page and to the right, essentially. Now we've got our slanted surface z equals x, and we've got our blue surface z equals 5. We've got the parabolic surface, that's our y equal x squared, and our yellow surface, which is going to be x equals 0. And finally, the very back here is our y equals 25. Now, you can see that that's not always the most clear way to try to sketch the region, and it may be a bit beyond this particular video as to how these surfaces are drawn, but using some space curves and parametric surfaces, you get a much more accurate picture of what this looks like. Here is that same solid region, but as you can tell, we have a very nice grid structure, and we aren't trying to overlap surfaces. They're only bounded to the actual regions of these curves. And there's our origin again, with our y equal x squared, our x equals 0, our z equals 5, our y equals 25, and down here with our z equals x. And that's what we've just calculated the volume of. So hopefully now you get a good sense of how we can actually take our methods of iterating integrals over rectangles and turn them into iterating double integrals over general regions. The first kind of trick is sketching the region on the xy plane and determining if it's x simple or y simple. Y simple means dy dx, and x simple means dx dy. Just make sure that whatever the boundaries on y are, if they are functions of x, then that integral needs to go first. We will integrate from y equals g1 of x to g2 of x so that we get an expression involving x, and then we evaluate the definite integral from x equals a to b, giving us a numerical result. The order is important, and we can't split up integrals the same way that we did over rectangular regions. Now, in a future video, we're going to be taking a look at regions that are not x simple or y simple necessarily, but might be very simple in polar coordinates, so stay tuned. Thanks for watching, and I'll see you in the next video.